Okay, good afternoon, everybody. Thank you very much for being here. My name is Pablo Machuca. I'm a PhD student at Cranfield University, and I am currently working under the supervision of Professor Joan Pau Sánchez. I am here to talk a little bit about the work that we're performing at Cranfield that relates to interplanetary CubeSats. The name of this project is Autonomous 3U CubeSats to fly by near asteroids. And I really hope that you find this work interesting and somewhat of a relevant contribution to the community. So for this mission analysis, we are particularly considering a 3U platform. And why is there so much interest in CubeSats nowadays? That is because they represent a movement towards a more affordable and accessible space industry through the standardization of spacecraft components. So some of the potential destinations that we are interested in might be the moon, comets and asteroids, and even other planets, as you have seen today. In order to reach these destinations, CubeSats will generally need to leverage a piggyback opportunity, whether it's a launch opportunity to low Earth orbit, or for instance, NASA's SLS, the transfer orbit to the moon. That's an orbit that will be used by the NEA Scout CubeSat, for instance. It's a 6U CubeSat, as well as other spacecraft that will try to observe and land on the moon, such as lunar flashlight. We had a presentation this morning. And then macro CubeSats that are already on their way to Mars were released by Atlas 5. However, one of the major challenges that interplanetary CubeSats need to face are the cost of ground operations. Well, in order to support the spacecraft in deep space travel, we need to use large ground stations, and we also need to pay the necessary workforce. And we hope to contribute to this aspect as well with this mission analysis. So the main goal of this project is to establish the feasibility of using 3 CubeSats to fly by near asteroids instead of the 6U CubeSats mission that has already been planned, the NEA Scout mission. In order to reduce the demand on ground stations, we also want to explore the possibility of using autonomous navigation. So one of the questions that we want to answer is it possible to reach near asteroids considering current propulsive capabilities? And then how well can a CubeSat achieve this goal? What are the flyby accuracies that can be achieved? And what is the potential scientific return that can be expected? The piggyback opportunity that we consider is a deployment from a periodic orbit around the center of Lagrange point, whether it is L1 or L2. Well, these piggyback opportunities are, of course, not as common as deployment opportunities from low Earth orbit or to low Earth orbit. But here there is a list of previous and also future missions that are planned to L1 and L2. And we can see a couple of missions that will be launched in a couple of years. And I believe NASA is also planning this mission called WG-FIRST that will also be deployed around L2. After being deployed around the Lagrange point, the mission that we are designing is using 1 or 2 maneuvers to try to encounter an asteroid that is passing near the Earth. And then as a footnote here, we do observe that current CubeSat capabilities enforce having long thrusting arcs. We cannot generate a maneuver an immediate change in velocity and instantaneous change in velocity. This needs to be taken into account for the trajectory design. However, as a first approach, we have seen that an impulsive maneuver model still holds as a valid approach to design trajectory. In terms of the navigation aspect, one of the constraints that we impose in the mission is that autonomous navigation will be carried out only collecting observations of the target asteroid. So as the CubeSat approaches the asteroid, you will collect observations of this asteroid, try to understand its position and velocity, and finally perform a trajectory correction maneuver before the flyby in order to fly by the asteroid as close as possible. In such a way, we hope to reduce the demand on ground stations yeah. So with the observations that we collect of the asteroid, the CubeSat will perform a final correction maneuver. We also propose a 3D CubeSat design using primary components that are already available or that have been used by previous missions. There is a lot of heritage here from the Inspire and Marco CubeSats, for instance the antennas, as well as the solar arrays that are provided by the same manufacturer as Marco solar arrays. Then we have JPL's Iris radio, and that will be used by Inspire and is used by Marco. Then as the propulsion system we consider Marco's 0.5 U propulsion system that is able to generate up to 80 meters per second of delta V. And then we see that approximately we'll have 0.8 U available for the science payload. In addition, we also constrain the mission to be less than 150 days, and this is to confine the effects or implications of deep space travel, such as radiation effects or thermal constraints if we travel very far away from the sun. So here are some of our results. First, in terms of the trajectory design, we observed that with the 80 meters per second that the propulsion system can generate, the resulting trajectories departing from the orbits around the Lagrange points resemble those trajectories on the unstable invariant manifold. So these are natural trajectories that do not require any delta V to travel on, and because the delta V that is available is very limited, the resulting trajectories are very similar. So in gray, or shaded gray, you can see the area that can be reached by a CubeSat departing from the periodic orbit within 150 days. And then we also included the asteroids that pass near that region between years 2019 and 2025. We have approximately 40 asteroids that pass near that region in the next 6 years. And then the second step in the trajectory design is to try to design trajectories to encounter those asteroids. We have observed that with only 80 meters per second of delta V, it is not possible to encounter all of them. But we do see that possible encounters exist for 24 of those asteroids in the following 6 years. For those asteroids that can be encountered, we compute delta V requirements and time of flights from different departure points on the periodic orbit. In terms of our navigation analysis, so one of the constraints is that we only collect observations of the asteroid for navigational purposes. This limits the number of asteroids that we can plan a mission for. For instance, if an asteroid is moving towards the sun, it is likely that we'll have an illuminated phase as seen from the CubeSat, and then we can collect observations of the asteroid for a longer period of time. However, if the asteroid is moving away from the sun, then it is likely that it will have a shaded phase, and it will not allow for an autonomous navigation strategy. So from this navigation analysis, we also reduce the number of asteroids that can be flown by. So we have 24 asteroids that could be reached with 80 meters per second, but then only 10 of them have such illumination properties that allow an autonomous navigation phase. And in this graph, what you can see, inbound asteroids that are moving towards the sun, are usually detectable around 7 days before the flyby, and then asteroids moving away from the sun are only detected around 2 days before the flyby. So in order to understand the flyby accuracies that can be achieved by a CubeSat, we perform a sensitivity analysis. We carried out multi-tower simulations that introduce errors in the initial position and velocity, in the implementation of the maneuvers, in directional magnitude of the maneuvers, as well as errors in the measurements. And with this analysis, we hope to understand what is the flyby accuracy that can be achieved. All of these errors are consistent with current CubeSat capabilities, either from other mission studies, such as Lumio, or then component specifications. So then, from this navigation analysis, we also conclude that flyby altitudes below 1,000 kilometers, which might sound big, but that's what it is. Below 1,000 kilometers are possible with current CubeSat capabilities. We're talking about 3U CubeSat. And then one of our other observations is that depending on when the correction maneuver, the final correction maneuver is implemented, the flyby accuracies will be different. So then, for instance, the bigger error ellipse that you see there, this is a B-plane representation of the flyby for around 1,000 cases. We can see that the biggest error ellipse is produced when we haven't collected enough observations of the asteroid and our estimate is not good enough. So then we have a big error ellipse. Then if we time that maneuver properly, we get to the solid black line, which is the error ellipse that would be the smallest error. And then if we wait for too long and we have collected too many observations and we have a very amount of time before the flyby, then the available delta V is not enough to correct the maneuver, and the error ellipse increases in size again. So then, just a brief discussion on the potential scientific return from such a 3U CubeSat mission, autonomous. We see that a modest scientific impact can be expected from such a mission because we have large flyby altitudes. That would be somewhere between 500 and 1,000 kilometers. The science payload that we consider was a visual camera and as well as a couple of spectrometers. With a visual camera, we will be able to achieve spatial resolution similar to those that can be accomplished from low Earth orbit. So we are talking about 30, 40 meters per pixel. However, we're talking about very small objects here, between 100 meters and maybe 2 kilometers in diameter. So then our images will be limited to perhaps 30 pixels per image. Spectroscopic observations could be used to determine the composition of the target asteroid and perhaps to evaluate space weathering effects as well. So then, as a conclusion of our project, we see that 3D CubeSats could be used to fly near the asteroids. Should we have the appropriate piggyback opportunity, and then, just limited scientific return could be expected from the mission, but it could still support efforts in the scientific community, for instance, to complement the objectives of a larger mission, or it could also help asteroid mining industry, for instance, to catalog potential targets of interest. And just a couple of conclusions of what I just said. We have designed trajectories according to current propulsion capability, that is 80 meters per second. And then we also constrain the mission to 150 days in order to propose a low-cost mission and not a mission that is operated during years, for instance. And then through our navigation analysis or sensitivity analysis, we conclude that flight accuracies between 500 and 1,000 kilometers are possible. And then, depending on the science payload, we will obtain some kind of scientific return from that mission. Some of our future steps is to increase the fidelity of the models that we have used. And we also would like to study alternative CubeSat missions, such as considering other piggyback opportunities, or understanding what would be the impact of having a bigger platform such as 6U CubeSats. And that is all. Thank you very much for your attention. Very much.
Okay, I'm interested to know that what is the time window of your imaging? Because the relative speed and velocity between this asteroid and your CubeSat is very high.
Yeah, so the time window for observations, when we have high relative velocities around 9-10 kilometers per second, the flybys usually last around 10 minutes.
Nice. When you calculated the 24 possible encounters, did you take into account the relative velocity of how fast the objects were going compared to how fast your CubeSat was going? Like, will they pass you way too fast?
Yeah, so as I mentioned, well, the CubeSat will only be able, with that limited commission span and the limited delta V velocities that you can achieve are only around 1 kilometer per second. Asteroids fly at maybe 10 kilometers per second, so then that yields large flyby relative velocities and a very short flyby. Any other questions?
Perhaps you already mentioned it, but so when you release from the L1 or L2, do you have a capability for waiting for a certain period for a certain asteroid you'd like to visit? Then how long is that?
So, well, we have not performed an extensive systems analysis. However, I guess one of the conclusions that we can draw from the analysis is that we have several flyby opportunities that are available. We have, in the next 6 years, we'll have a total of 10, or at least 10 opportunities. So then, we're hoping that we'll be able to either wait inside of the mothership spacecraft and wait for one of those opportunities. It will be perhaps less than a year of waiting time. I'm not sure if that's possible. Any last questions? Thank you.